Thank you, Raf. Thank you so much. All right. So first of all, let me thank the organizers for giving me this opportunity to talk about some of our work. It has been a wonderful workshop. So let me begin. So what I'm going to talk about today is some of the bounds, universal bounds that we have found on fluctuations in the context of continuous and discrete thermal machine. So this work is done in collaboration with my students as well as my external collaborators from various places. So I'll be primarily focusing on these two first references. And the third reference that I've given here, I'll going to talk very briefly about it just to set the stage. Okay, so let's begin. So the plan of the talk is I'm first going to give a brief introduction on thermodynamic uncertainty relation, and then go on to talk about bounds on fluctuations and how our study connects the TUR, the thermodynamic uncertainty relation, in the case of continuous thermal machines, which are autonomous. And the second situation I'll consider when the thermal machines are could be continuous or discrete, but they are driven. Okay, they are non-autonomous. And then I'll summarize my talk. Okay, so since it's a workshop of stochastic thermodynamics, I think I don't have to motivate about fluctuations. In fact, it's all about fluctuations, and we know that fluctuations are in fact not arbitrary. For equilibrium systems, we know that there is a well-known universal fluctuation dissipation relation. So just to put that in our context, imagine if you have a system which is in contact with two baths which are at different, let's say, chemical potential, and as a result, there is a charge current that flows. Then, of course, you can, in the steady state, you can write the current in terms of the chemical potential difference or the bias voltage, which is of this form. And you can also write the fluctuation. So this J square C refers to cumulant, which is like the fluctuation, the current fluctuation, which you can also express, which has a equilibrium fluctuation component as well as various non-equilibrium component. Now, what fluctuation dissipation theorem essentially tells us is that the equilibrium fluctuation in the charge current is essentially related to the conductance. So that is the standard fluctuation dissipation. So in that sense, of course, we can say fluctuations are not arbitrary, but things don't stop here. We also have universal fluctuation relation over the several decades. We have now well understood fluctuation relations quite in detailed form. And what in this context fluctuation relation essentially establish at the level of probability distribution, this is the relation it gives, which essentially tells you that the probability that in a given time interval, if you look at n electrons flowing from high bias to low bias, that probability is exponentially larger than probability of electron flowing in the opposite direction. And as a result, what you can actually show is that not only you have relations between linear transport coefficients, namely S naught connects with G1, which is the standard fluctuation dissipation that you knew, but there are higher order coefficients getting related as a consequence of these fluctuation relations. So in this context, involving this fluctuation, there was a very interesting relation that was given, which in fact was talked about in this workshop in the first day, is known as the thermodynamic uncertainty relation, which is nothing but a trade-off relation, involves square of the relative fluctuation and entropy production rate. So if you look at any particular current and construct the relative uncertainty of this current, what this relation tells you that you cannot arbitrarily reduce this relative uncertainty. Rather, you have to pay a cost, and that cost is given by the entropy production. And now, this particular bound was initially derived for in the linear response regime systems in steady state, but it was then later generalized also beyond linear response in the Markovian dynamics and so on and so forth. And traditionally, this relation, as long as system is in the linear response, it holds true for any type of current that you look at. So what are the implications of these relations? So one of the implication is in the context of thermal machines that arises. And the question that comes is that what is a good heat engine? So you typically expect you want to have a large power output, you want to operate the heat engine close to Carnot efficiency, and you want small fluctuation in the power output. Now, the implication of the thermodynamic uncertainty relation is that all these three conditions or three requirements are not compatible with each other, and there was a wonderful bound as a consequence of TUR was given, which is by Udo and Pietzonica, given by this, which essentially tells you that if you want an engine operating at Carnot efficiency at finite power, you have to sacrifice the power fluctuation, so that can diverge. So this is known from the thermodynamic uncertainty relation. Now, what are the questions that we asked? So that brings me to the central topic. So let me first talk about the continuous thermal machine, which are autonomous. So what we asked in this context is that are thermodynamic uncertainty relations, which you can write for various currents, are they independent? So in that context, I can, for example, think about a steady state junction, which is a thermoelectric. So I can talk about two different currents, charge current and heat current. And I ask the question whether the TUR I can write for both the currents, whether they are independent or not. And the answer turned out to be no. That these TURs for different currents are not independent. Rather, there is a hierarchy. And this hierarchy arises whenever you put an operational condition, that whenever you want this device to do some useful, as a useful machine, it gives you that hierarchy. So let me just briefly point out that. So if you consider a two affinity problem, then in the linear response regime, of course, you have the Onsager principle. You can write the current in this form. On top of that, if we assume time reversal symmetry, then the central ingredient that goes here is a relative uncertainty. We are looking at relative uncertainty for individual current. And remember, it's a two affinity problem, so I can talk about two different currents. And the most important quantity is the ratio of this relative uncertainty. So I have 1 and 2, the two currents, which in the linear response I can write in certain form. Now, the most important ingredient is that if I impose the condition that let the setup operates as a useful machine, like it can either work, let's say, as a heat engine, or it can work as a refrigerator, then you can always consider one of the current as input. Let's say I talk about an engine, so I can take, if I take, if I think of a heat engine, then I can take heat as an input and work as an output, right? So heat current would be input and work current would be output. So if I impose that condition, you get something remarkable, which is that this ratio of the relative uncertainty is greater than 1. So what it essentially tells you that the relative fluctuation of output current is always going to be larger than input current, okay? So in the context of engine, it would be the relative fluctuation of work current would be larger than relative fluctuation of input current. And as a result, you right away actually see a hierarchy in TUR emerges, because entropy production is positive, which if you work out, I mean, you trivially get this relation as a, so if your setup is working in a useful operational regime, you get this hierarchy in TURs. So which in that sense are not independent. So in the context of engine, the TUR of work current is higher than TUR of heat current, which is greater than 2. Now, as a result, what turns out is another very useful relation, that if you construct a ratio of fluctuations of work and heat, so which I call eta 2, and this is going to appear in next slides as well. So please pay attention here. So this eta 2, which is a ratio of output fluctuation over input fluctuation, this gets bounded. This has both lower and upper bound. And lower bound gets decided by eta average, the average efficiency, and upper bound gets decided by eta c square. So, and this is consequence of a continuous engine. So what we receive is universal lower and upper bound on ratio of fluctuation. And if you look at this relation, you can also think of this relation gives you a new bound on average efficiency in terms of fluctuations, which is tighter than Carnot. So all of this is for continuous engine in the linear response. And as I said, this is true for any operational regime. So it need not to be only heat engine, but it can be also a refrigerator. And if you construct accordingly the ratio of fluctuation of output over input, you're going to get both lower and upper bounds. And this is one of the sort of result that I'm showing, numerical result for a particular setup where we basically take a single dot coupled with two reservoirs, and it's a you can think of a thermoelectric setup. And then if you look at this lower, so this is the lower bound on eta 2 and this is an upper bound on eta 2, and this particular regime where this bound is getting satisfied. So whenever they satisfy engine condition, so that this is the regime where engine condition is satisfied, and this bound is becoming valid. And same goes for the upper bound. Okay, so this has been for the continuous autonomous case. But what happens if I drive the system? The question that we ask: does this how robust are these bounds? Do they also satisfy, or are they also valid if the systems, if the thermal machines are non-autonomous? So that was the question. So in that context, we considered two different types of non-autonomous engines. So one is a non-autonomous continuous engine, where your system of interest is always connected with two baths, but it's externally driven, and a non-autonomous discrete machine. So we particularly focus on Otto cycle, which I believe all of you are aware of. So let me highlight what our observation for a non-autonomous continuous engine. So here what we took a toy model, which is as simple as a simple two-level system coupled with two baths, and it's periodically driven. And we essentially go to the steady state, the periodic steady state, and we start looking at the TUR bounds as well as the bounds on eta 2, the ratio of fluctuation. So if you look at the inset, let's look at the inset where you are in the operational regime of engine and you have this eta 2. What you notice is that this eta 2 is greater than eta average square, which is the red line here. So that is good. But if you compare with eta c square, so eta 2 is supposed to be, in continuous case, eta 2 was less than eta c square, but that is not true here. Okay. So what you right away see is that if you drive the system, or in the non-autonomous continuous case, what you see is that the lower bound on eta 2 is getting satisfied, but the upper bound is violated. Okay, so this is so here the delta is the frequency of the modulation. And if you look at the outer plot, I'm plotting the refrigerator when the setup is working as a refrigerator. You see that the lower bound is getting violated, but the upper bound is getting satisfied. So the trend has been opposite for engine and refrigerator. Okay, so in engine case, you see lower bound is getting satisfied. For refrigerator, is the upper bound getting satisfied. Okay, so that was one observation that we saw in this situation. But what about Otto cycle? What about if I go to the Otto cycle, the discrete non-autonomous situation? So we again took certain toy models. So here is an example of a two-level system and executing an Otto cycle. And I'm plotting the lower bound, eta 2 minus eta average square, as a function of u, where u is the non-adiabatic parameter. So in fact, u is 1, that corresponds to adiabatic regime, and not equal to 1 is a non-adiabatic regime. And once again, what you see is that the lower bound is getting satisfied when it is working as an engine. Okay, and as a result, of course, the hierarchy, the TUR hierarchy also arises. Same if I take a parametrically driven harmonic oscillator, I once again see lower bound is getting satisfied. So in the engine regime. But if you look at the upper bound, once again, in the engine regime, the upper bound is getting violated. Okay, so as I said, for the continuous case, even for the discrete Otto cycle, the lower bound for engine is getting respected, but upper bound is getting violated, and the opposite trend is observed for the refrigerator case. So this is not the same situation as the continuous non-autonomous situation. So it's highlighting essentially the difference in the nature of fluctuations. So that brought us sort of to the question that why this is emerging, why this is happening. So that led us to sort of look at this kind of non-autonomous system in a little bit more detail. So we went ahead and start looking at this Otto cycle and tried to develop a very general theory. And of course, since we need both all the currents and their fluctuations, so we tried to develop the full statistics for a general Otto cycle. So just to remind you, our Otto cycle is a 4-stroke cycle that we are considering, which has 2 unitary strokes and 2 thermalization strokes in contact with hot and cold bath. So here, the unitary strokes are driven by some Hamiltonian H1, and lambda is the driving parameter. And given that, of course, you can construct the full statistics of work and heat following the two-time measurement protocol, which we do here. And what we are trying to do here is to construct a linear response framework given the full statistics. Okay, so linear response framework would be what? You essentially take the driving parameter, you do the small amplitude expansion. You take this lambda 0 minus lambda 1, that to be small. So that is like your one of the driving force. So that is small. And another small parameter would be the temperature difference. So that is how you can go to the linear response. So in order to develop this full statistics, we essentially take into account the Schwinger-Keldy's formalism, and we obtain an analytical expression for arbitrary working fluid. And of course, one can verify that this setup the Otto cycle satisfies the fluctuation symmetry. Now let's go to the linear response. So once you have the expressions for current and fluctuations, you can try to identify the entropy production and try to go to the linear response. So entropy production, you can identify two affinities. So one of the affinity is due to the amplitude of the driving, the difference of the amplitude of driving, and another affinity is due to the temperature difference. And you have two currents, work current and heat current. So you identify the entropy production, and you can write these currents, if you're in the linear response, you can write in terms of the Onsager coefficient. So for this general Otto cycle, we were able to find expressions for this Onsager coefficients, which are given in this form, where if you look at the entire response functions are governed by this quantity G, which is nothing but the correlation function due to the perturbation. So it's essentially the correlation involving H1, where H1 is the perturbing Hamiltonian. So you get essentially the response function. And this, if you now look at how these response functions are related to fluctuation, typically you expect that if and expect a classical fluctuation dissipation type relation. So what happens is that for heat current, it satisfies the standard fluctuation dissipation relation, that the response is equals to the heat fluctuation. However, the most interesting observation is that uh, the work fluctuation, that doesn't satisfy the classical fluctuation dissipation relation. In fact, there is a breakdown of that relation, which precisely happens because the unperturbed Hamiltonian and the perturbed Hamiltonian don't commute. If they commute, then of course you're gonna get the classical FDR type relation. And this is the fundamental reason why you actually see the opposite trends in the engine versus refrigerator. So that in one case, that lower bound is getting respected, but for the other case, the upper bound is getting respected. So that is, so this violation of fluctuation dissipation for the work current is the main reason for this observation. So as a result, lower bound is violated for refrigerator, but upper bound gets validated. And we observed that we took a particular example where we had n bosons trapped in a harmonic trap, which is executing an Otto cycle. So this is the bare Hamiltonian and this is the perturbed Hamiltonian. So what you see is that if you now are in the engine regime, you see nicely that this ratio eta 2 by eta square, this is less than 1, which indicates that the lower bound is getting respected, but upper bound is getting violated, which is this is the violation regime. Whereas in the refrigerator regime, you see the opposite trend, that the lower bound is getting violated, but upper bound is getting respected. So that essentially brings me to the end of my talk. So what we essentially showed is that if you are in the useful operational regime of any machine, either be engine or refrigerator, the TUR relations for different currents are not independent, rather they have a strict hierarchy. And what you see is that the relative uncertainty or TUR of output is always larger than the TUR of input. And that for the continuous, that essentially leads to a bound on the ratio of fluctuation, which we call eta 2, both lower and upper bound, which you get for continuous engine. But this bound doesn't get respected if you have non-autonomous engine. And precisely due to the violation of work fluctuation dissipation relation, you see a different trend whether you are whether your system is operating either as an engine or a refrigerator. So for engine, for example, lower bound is getting respected, but upper bound is violated. And for refrigerator, you see an opposite trend. So with that, let me thank you for your attention.